Hello, everyone. How are you doing? So I hope you can hear me because hindi ako nakapagdala ng ano ng sound equipment. So uh I'm just using my laptop's microphone uh for hosting. So please uh move to the next slide. So how are you today? No? So give us a reply on the chat. No? If you are just happy because you're still surviving uh the Tuesday, so kahapon, or are you just chilling out there? Or you're so happy. Happy World Quantum Day. Or you're just as excited. Superposition of one and three. Oh, that's cool. So let's get the numbers coming. So for our Spotlight Talks session number three, okay, kindly uh move to the next slide. So our esteemed speaker is a postdoctoral research fellow at the Center for Quantum Technologies in Singapore, leading the research and development in quantum sensing, precision measurement, and next generation gravimeters. He earned his PhD from Technische Universität Wien in Vienna, Austria, with the Sub Auspiciis Presidentis, or highest national distinction, and holds an Erasmus Mundus Master of Science in Photonics. Furthermore, he is the co-founder of Toulon Photonics and technical advisor at Quantum Defense Innovation. Previously led the, take this, 500,000 euro Future Lasers spin-off project. Wow. Also, he holds four international patents, including breakthrough laser frequency stabilization technology that significantly outperforms current industry benchmark. And he's dedicated to translating frontier science into real-world applications and advancing physics education and research across the ASEAN region. So please help us welcome Dr. Fritz Diorico. A round of applause. A virtual round of applause, everyone.
Hi guys. Can I share my screen? Hello. Hello. Can you guys see my screen? I'm sharing my screen.
Not yet, Doc.
Not yet.
Oh, there you go.
There it is. Okay, I think there's a lag. So yeah, can I begin my talk?
Yes, Doc, go ahead.
Yes, so yeah, thank you for that warm invitation and well, introduction, and thank you also for this invitation. I'm Fritz Diorico, so I'm actually I'm a real quantum physicist. I special can everybody can hear me, right? Like just let me know if I'm just talking and nobody can hear me. I think everybody can hear me. So yeah, I'm actually a real quantum physicist, but I think I think of myself more of like an engineer. So this talk, I'm not really going to go into detail on everything or quantum computers. I'll touch on quantum computers. Actually, in fact, I'll go into detail on, let's say, surface level quantum hardware, but I'll focus more on my journey, like where I started, and it's I just want to I hope I can inspire other people to follow my path, or maybe even like go beyond. And yeah, it's it's not easy being a Filipino scientist, engineer, physicist, going abroad. But yeah, nonetheless, my the title of my talk is actually ironic because I call it I really want to strike a point because I'm not really fond of the quantum hype. I'm a quantum physicist, but there's a lot of hype to quantum, and I'm very, let's say, how would you call this? I'm very careful as to when to use it and when is the right time not to use it. So yeah, I like practical quantum technologies, and quantum computers is one of them. But it's not just quantum computers, and I'll actually get into that. So, but before that, let me give you an introduction about myself. So I grew up in Cebu City, Philippines. That's where I did my undergraduate, so at the University of San Carlos. It was a long, long time ago. And then as was already introduced, I was fortunate enough to get this Erasmus Mundus scholarship. So this was a very, how would you call this? It was a very, let's say, eye-opening experience. Because without it, then I would probably be still in the Philippines. So I don't know, maybe I might have found another way to study abroad, because it's not really easy to get abroad. And there are some ways, and if you're interested, like just contact me. I know some of the opportunities in Europe mostly. So yeah, I spent 2 years, 1 year in Belgium and then 1 year in Scotland, and this was really hardcore photonics engineering. Photonics is just optical engineering, but in a sense that nowadays photonics is the future of computing, actually, and I will get into that. And it's related to AI. It's also related to quantum. But I really like quantum physics. I really like quantum theory. So I decided to do a master thesis in theoretical physics. And yeah, it was because I wanted to, I felt like theoretical physics was something that I didn't really have enough training growing up, or at least, you know, we didn't have enough resources. And my train of thought, or at least my personality, is always that I want to work on the things that I'm weak at. So I don't want to stick to my strengths. I want to work on my weaknesses. So yeah, that was me a long, long time ago. I was still a bit chubbier and I had a lot more hair. So yeah, I always make this joke that PhD actually means permanent hair damage because I lost a lot of hair, but yeah, that's maybe unrelated. So yeah, then I did a PhD in Jörg, the Austrian German name, Jörg Schmidmeyer's group at TU Vienna. So people often call it Technical University of Vienna, but the German name is Technische Universität Wien. Yes, I my PhD was the topic of my PhD was actually hybrid quantum systems, cold atoms, and superconducting circuits. I won't touch into that, but I won't talk about my thesis, but I'll give an overview later why that's important and why that is actually becoming more relevant now. Now, I was part of the uh, Complex Quantum Systems doctoral program. So now it's called the VCQ doctoral program. And I was very fortunate enough to be, well, I don't know if I would call it fortunate because Anton Zeilinger, the Nobel Prize a few years ago, was the one organizing the doctoral program. And he was the one organizing the interview with the other professors. So it wasn't easy. It really wasn't easy. And it was funny because they interviewed us. Uh, the way they interviewed us was AI safe, and at that time there was no AI because they gave us random papers that we had to read, and then we we didn't know what those papers were, so they just gave us a few papers, and we could choose out of those 5 or 10 papers, and they put us in a room. without anything, no internet, just pen, paper, blackboard, nothing. And we had to read and understand that paper. And after I think it was 1 hour, somebody took us into a big hall where in Vienna, where apparently Erwin Schrödinger was doing all of his blackboard like calculations because Schrödinger is from Vienna, Austria. And Anton Zeilinger said, "Oh, like you're in Erwin Schrödinger's like blackboard. Like so, where you're writing right now is Erwin Schrödinger's blackboard." And basically, for 2 hours, you were just trying to discuss the paper. And yeah, Anton Zeilinger and his professors, including my supervisor, grilled us with questions. So that was my experience. It was interesting because now, if I think about it, yeah, like it's AI safe because now it's very hard it's very hard to see like discern what is human and what is AI, especially if it's remote. Like the only way to test is in real life. So then after that, I did a postdoc with Unur Hosten. So that was 6, 7 years ago. And Unur Hosten is actually coming from Stanford University. And there is a new institute in Austria called the Institute of Science and Technology Austria. And by the way, look them up, look IST Austria, because they have PhD programs. It's very competitive though, but look it up if you want to do a PhD. It's okay for IST Austria for you to apply for a PhD with just a bachelor. So you don't need to have a master, although master helps. But yeah, and they're like IST Austria spans physics, AI, computer science, chemistry, everything, neuroscience. The institute started as a life science medicine research center, and they expanded to physics in the last 10 years. And yeah, so Onur was a new professor there coming from Stanford University. He comes from the Mark Kasevich group. So Mark Kasevich is a very prominent physicist in the quantum sensing or the quantum physics world because Mark Kasevich and Unur Hosten has the world record for spin squeezing. So you probably don't know what that is. A spin squeezing is just a way that you can actually enhance quantum measurement uh, to sense beyond the classical limit. So it's a way that you can actually just make sensors that are much, much more sensitive. And Unur's group is actually called Quantum Sensing Lab at IST Austria, and he wants to do sensing beyond the classical limit. So I was Unur's first postdoc. I mean, just me and him building the lab out of nothing, assembling lasers, vacuum chambers, soldering electronics, writing programs. So, as an experimental physicist, we experimental physicists, especially the really good ones, I'm not saying that I'm good, but we are all around engineers. Like we can do everything because we're forced to. It's something that we have to do. We have to know how to write code, to talk to instruments, gather data, synchronize all the instruments, also design analog circuits, FPGAs, everything for experimental control. And in addition to that, vacuum chambers, lasers, and laser cooling, trapping atoms, so on. So yeah, quantum technology. So I put here like in asterisk quantum. Like I put it that this way intentionally because I mean quantum technologies. I shouldn't really repeat quantum, right? Like I could just say computers, sensing. And the thing is nowadays, like everybody's just attaching quantum into anything, and it doesn't really mean anything. I'm not saying that quantum like is bad, but uh, I want to hopefully answer some of the questions that you guys asked it from the previous speaker. Like he gave amazing answers, actually very, very safe regarding like what can quantum do and what can quantum like not do. Like what is quantum's purpose, quantum computing's purpose really in this world. And also I'll touch on quantum sensing and also the last part, time frequency distribution, GNS, global navigation network systems and all of that. Because for me, like these last two things, quantum sensing is actually the most practical quantum technology. But the funny thing is, all of these are connected. Like you can turn a quantum computer into a quantum sensor. You can turn a quantum sensor into a quantum computer. They're using exactly the same hardware, same physics. So if you look at the real world, although quantum computers are the ones that are making the news, but at the background, it's actually the quantum sensors that are making more practical applications. And I will touch into that. So quantum technologies, here is a nice AI generated image. Of course, I did not make that. I just want to be honest. But before I proceed, I would like to pay homage to all of the famous quantum physicists. So these are the famous quantum physicists. I'll just flash them there in history. To the best of my knowledge, who had, let's say, who impacted quantum technologies or all of the quantum computing, quantum hardware infrastructure that we have these days, nowadays. And if I forgot something, yeah, I apologize. And the ones that I put in bold are actually the ones that I met in person. And Serge Harosh, Anton Seilinger, that guy interviewed me. I also met John Martinez. So I don't know if you know John Martinez. He was the one at Google. He started Google, the Google quantum computing infrastructure, but now he also has his own startup. I actually have a good friend that works for John Martinez, but yeah, now we have paid homage to the godfathers of quantum. Now we can proceed. So quantum computers, you probably know what this is. So I apologize in advance if this is something that you already know. But what makes a quantum computer special is that this picture on the right, the qubit. So the qubit, for me, as a quantum physicist, I would not call this a qubit. I would just call this a block sphere, and it's a something. It's a tool that you can find in any quantum system. Anything. If you just look at molecular transitions in chemistry, atomic transitions, an energy, an excitation in a quantum dot, or anything that has quantum effects. Now, the interesting thing here is that how I always explain this, and I hope I will do a good job because this is a very, difficult topic to understand. Actually, it's not more the understanding, it's more the accepting. Like if you just accept it, it's okay. So how I explain this is that for a quantum bit, what you have is just you still have binary information. You still have binary information, although you can actually have qubits, qdits. Your parameter space can actually span more than 2 degrees of freedom, because here with a bit, you just have 2 degrees of freedom, right? Either you're 0 or 1, you're up or down, you're north or south. But for a quantum computer, for a quantum state, the state is actually a vector. It's an arrow pointing someplace in the sphere. So if you imagine planet Earth, so the North Pole is, let's say, one state of the bit, let's say in this picture, 0, and then the South Pole is actually 1. So those are your, let's say, classical bit orientations. But then you can imagine like, oh, what about Philippines? Like, what about North America? And you can imagine like the state vector of those, let's say, locations give you a different superposition or possibility of your quantum state. So if you think about it, then you have infinite possibilities between 0 and 1 or up or down. And that pretty much changes how you think of computation. So I should actually put a picture of Richard Feynman here, because actually Richard Feynman was the one who really inspired quantum computing. Like just with a few sentences, he said something like, like we are building things so small, we're able to nanofabricate metallic structures and make currents, electrical currents go into tiny places. Eventually, when we have to compute, we will have to use the laws of quantum physics. And he was actually hinting towards the quantum computer. And that's pretty much exactly what happened. Because now, if you think about it, just with this simple picture, how do you actually do computation? So now if this is your, let's say, information space, that is your bit space for 1 qubit, how do you meaningfully do computation? It was like somewhere like 20 years ago when they started writing algorithms like the Shor's algorithm and factorization, things like that, and many things that could be done faster. So I won't get into that because I'm sure somebody else like knows that better than I do, but I want to talk about the hardware because I love engineering. I love hardware, like real hardware. So right now, to the best of my abilities, there are, oh, sorry, three main environments or ecosystems for doing quantum computations. You probably know this, like the electron-based, those are your superconducting circuits, your superconducting computers, and they are contained in refrigerators that are so expensive. So IBM, Google, Amazon, and so on. And there are also other non-superconducting quantum computers where they're doing more like spin qubits or these spintronics. So basically, this is actually using the spin of the electron as a degree of freedom instead of using an artificial atom, which is this superconducting circuit. There is also quantum dots. And then there's also actually I'll touch this more first. Cold atoms and ions. So you probably know this maybe a bit, like if you've heard of the company Quantinuum. So I'm actually applying for Quantinuum, fingers crossed. So yeah, so this amongst other companies, they are dealing with real atoms that they're trapping. They're really trapping atoms in physical space and they're laser cooling them. And this has its own advantages. So I'll come to that a bit later. And then there's also photonics. So this is doing quantum computation with light, lasers, free space optics, or integrated silicon photonics, photonic integrated circuits. And this is photonics, like this part is actually much faster. And it's also very nice because it hints toward like all of the infrastructure for photonics or photonic quantum computation can be used for other applications. So I will come into that because all of this quantum computing infrastructure, you can actually repurpose them for other applications. Like for example, you can use the hardware, like the hardware that you develop for them can be you develop faster FPGAs or faster electronics just to control your superconducting, your IBM quantum computers. And at the background of it, they are actually selling that hardware for other applications that are non-quantum. So that's actually where the money really is. And yeah, so electron-based systems, you've probably seen these if you watch an IBM or a Google introduction to quantum computers talk. So these are just some of the some pictures of the different architectures or ecosystems that you can use. And the nice thing here is that it's very, very scalable because we can use our existing all of our existing nano fabrication. So everything that the TSMC, Taiwan Semiconductor Corporation, Manufacturing Corporation, everything that they can do, like for producing our GPUs, our Intel processors, you can also use to produce these circuits. So that's why it's very, very scalable. But there's a downside to that, and I'll come to that a bit later. And now there's the cold atoms and ions. Now, these are very difficult to make. It involves a lot of lasers, a lot of electronics because you're really physically holding each atom with lasers or optical tweezers or optical traps, and you have to put them in place and you have to operate on them. It's a nightmare, but for some reason it's actually working. There are actually startups, and not startups anymore, companies that are doing this very, very efficiently. And there's photonics. So I told you about this. And the nice thing with photonics is that right now it's exactly the same. You can use exactly the same infrastructure for fabrication, nanofabrication for semiconductors for photonics, because now you can actually make photonic circuits. So instead of electrons, you have actual light moving in a waveguide instead of a wire. And now light is what you use for doing computation. And you can obviously do quantum computation. So the nice thing here is that if you build a quantum computer out of photonics, you can also do classical computation, photonic computing. And photonic computing is amazing because it's incredibly fast. So yeah, quantum computing is really a technical nightmare. picture I showed here. So this is Google on picture on the right. On the bottom is one of the early ion quantum computers, I would guess. Picture on the right here, sorry, far right, your right, yeah, our right, is a picture of my experiment in Austria, in IST Austria. So yeah, it's I won't talk about this, but what we were doing, I won't go into detail, but we were not building a quantum computer, but we were building a very ultra sensitive sensor. So a sensor that could actually detect gravitational waves, maybe like push sensing beyond the classical limit. And my mentor, Unur Hosten, he wants to detect, it's very, very ambitious. He wants to detect gravitational waves and he wants to even measure hints of gravity being quantized. So actually quantum gravity, it's very, very difficult. So all of these things I showed, but I didn't really explain like why it's relevant. And this is actually a very, very nice plot. Sorry, I'm just going to switch on my lights briefly because it's getting dark. Sorry. Okay, I'm back. So you might have seen this plot before. So this plot is pretty much how we physicists argue and engineers argue within ourselves, like what is what, why is this good and why is that bad. So on the top you actually have you have size, and then middle you have the coupling rate. So just think of the coupling rate as your gate time or your computational time, or your in if it's a computer, it's your processor speed, your like your clock speed. And the uh, bottom row is actually coherence time. So this is how long your qubit stays coherent. And what that coherence time just really means, how long a qubit remains readable. Because a qubit, if you store it in a quantum memory, in a superconducting qubit, for example, it won't stay long. And you can already see here that for our current infrastructure, superconducting qubits, which is IBM, Google, and so on, you can have very, very fast coupling rates. You can do fast computation, but your coherence time is incredibly low. I mean, now they have error correction algorithms like to improve this. They all are also trying to improve, excuse me, the hardware, but your computational time is few microseconds, your coherence time. So it's very bad. So if you store the qubit and then for later use, and then you do computation, and then you come back to your qubit has already forgotten itself, or it's lost, decohered. So that's very bad. But now if you look at this plot, on as you go larger and larger in size, sorry, smaller and smaller in size, it's actually interesting because the coherence time increases. But okay, your cup there you cannot get the best of both worlds, so your coupling rate is also slower, but your coherence time is much longer. And if you even go beyond like a nuclear spin, like an actual nucleus, it's hours. So that's insane. But okay, it's very hard to excite a nucleus. So there are only two ways. You either split a nucleus, but then you would get an explosion. That would be a nuclear explosion. Or you excite it with a laser. And actually, Thorsten Schum here, you can also look him up. He was also one of my PhD mentors. He actually did this. So this is his main topic of research, and he and his colleagues were the first one to excite the nucleus of the atom. They used thorium with a laser, because ideally you would use a nuclear reactor or a neutron, and then boom, you get an explosion. Well, not exactly, but yeah, something like that. So yeah, the now when all of this quantum computing, uh, let's say hardware or companies were coming out, they all started with the superconducting ecosystem. So yeah, IBM, Google, and then now you have atoms, ions, like continuum, and there are a lot of neutral atom or neutral or ion uh, uh, quantum computing companies that are getting much more relevant because it seems like all roads lead to a hybrid quantum system. So which is basically all of these talking to each other. So you use your cold atoms or your ions as your quantum memory, and then you use your electron-based systems as for your computation because you can do it faster there. And then you could also do photonics for both, but you can also use photonics to actually send qubits because photonics gives you the opportunity to use your existing optical fiber infrastructure for our internet for a future quantum internet. And but yeah, of course, like these things are still very, very far in the future, but hopefully one day. And yeah, for my PhD, we actually tried to build a hybrid quantum system. So this is just showing here like a quick picture of our experiment. So we tried to combine cold atoms and brought it into a superconducting, uh, we brought it into well, we brought it into a superconducting environment. So on this science chamber, it's actually it's a cryostat. So we could in principle have cold atoms talk to superconducting circuits, and the main goal or main dream was to really use the cold atoms as a quantum memory and then use the superconducting infrastructure right beside it as computation and so on. And yeah, this is just showing pictures of my experiment. So this was actually fun. It's me. So it was quite involved. So the picture on the far top left is our control system. And we're very proud of this because all of these LCD monitors we actually harvested. They were just in the trash. And then we opened it up and we realized that, it's not really broken. There's just a specific capacitor in the power distribution board that breaks, and all you have to do is replace that, and then poof, voila, like you have like free LCD monitors. However, it's not so true anymore with the new PCBs because they make everything too integrated, so it's very hard to spot which component is broken. So yeah, this was our experiment. It was a very interesting experience. Now I'm going to, I have to like you can still see this annotation, right? So I think I'll erase it. There we go. So yeah, so now I'm going to switch gears a bit. I'm going to talk about quantum sensing. And I hope that you also find this interesting because for me, I don't really like to like when people say like, oh, I want to invest in quantum computers, or I want to learn quantum computers. No, 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 no. Learn or invest in quantum technology. So I actually am very, very adamant about this. Like if I'm a bit nationalistic now, so if Philippines should invest in quantum technologies, not just quantum computers, because the more practical things like the technology that you develop for quantum computers, you can also use them for quantum sensing. So yeah, what is quantum sensing? What can you do with quantum sensors? So these are just pictures, like just like real, let's say, research or work, not research, but companies that do this. So picture on the far bottom right, like in this mountain, I think it's Mount Etna. So this is a gravimeter. What it is just measuring uh, it's just measuring gravity extremely accurately, and it doesn't have to be gravity. Like for example, these NV diamond. So diamond, which is also now a quantum computer infrastructure, it's also an extremely ultra sensitive magnetic field sensor. And now there are even MRIs that are now integrating these NV diamond quantum sensors. And you can also use it for just measuring anything. And of course, like it doesn't have to be it's not always practical because most of the time, like for if you think business, then you have to think like, oh, is it better than what I can buy, or is it what do I gain at the end? And basically, what this is instead of in quantum mechanics enhancing computation, it's quantum mechanics enhancing sensitivity beyond the classical limit. And this is very, very interesting. So I hope that everybody also gets excited about this, although it's not computing per se, but it's exactly the same hardware. And so at Austria, my last few years, last 7 years in Austria, Unter Hosten, he, as I mentioned, he wants to entangle atoms, cold atoms, with gravity. So very, very ambitious. And in doing so, we have to develop a lot of optics. So Vyacheslav Lee here, this is taken from his thesis. So one of the first PhDs that I supervised. And this here is like, yeah, a schematic of our setup, just actually a very small part of it. Yeah. Uh, so yeah, basically as a physicist, I have to deal with an experimental physicist. I have to deal with all of these things. So yeah, I'm good at many of these, but there are some that I can just do basic things. Like, for example, like we also have to draw our own like mechanical engineering schematics. But most of the time, like when we send it to the engineer, like the engineer has to redraw it, but it helps if we already understand how it's fabricated. And yeah, so in the process of doing this, I'll talk about my last few years. So we deal with a lot of lasers. So laser physics is here, quantum physics, but the thing is like lasers are very, very, let's say, like people, when I have a friend who told me like, oh yeah, I heard about lasers and what are they used for quantum. So now I'm just going to switch gears a bit and talk about lasers. So laser is just a very single color flashlight. So it's very, very single color, but they're not really that stable. So you often have to tune it, and it's like you're tuning your voice, like it's like you're tuning your instrument to a tuning fork. But for lasers, this would be atoms, molecules, or another laser, or optical resonators or optical tuning forks. And yeah, I won't go into this. Like, sorry, I apologize, guys, because I didn't have time to. I will be honest, I didn't have time to prepare this talk because I'm very busy. But so I just took the talk that I gave last from San Carlos. This is going a bit more into detail, but I won't talk much about it, but basically, just to give you a teaser on what we built. So we actually, in Unor Hosten's group, we accidentally came across a new way to make a laser much more stable. And this is pretty much how it works. If there's a physicist like who understands this amongst you, like feel free to ask me later. But just to give you an example, for all of the laser frequency stabilization techniques that exist out there, so lower in the y-axis is better. This is our method, so in red. So it's already better than most other techniques out there. So, and we use this technique now in Unor Hosten's lab. And yeah, this is the startup that we made. So, well, actually, I'm almost done towards the end. So this was accidental because a psychologist friend asked me, like, what is your laser, this thing that you invented, what is it useful for? And that really pushed me to ask questions whether this can be turned into a startup. So yes, we did that. I got this grant. We built prototypes. Now the startup is in stealth mode. There's a new CEO. I can briefly touch on it later why, but yeah, these lasers are very, very useful for quantum technologies, quantum computing, sensing, also for sensing, like a lot of laser remote sensing, and actually also for satellite communications, because now all of satellites are now talking to each other via laser. And the lower noise laser you have, if your laser is so ultra low noise, then you can cram in more information. And Starlink, for example, is talking to each other via laser so that it increases bandwidth dramatically. So I won't talk into this. Uh, so yeah, I'm think I'm pretty much done. So I actually added a few slides here because there were a few questions earlier that was very, very interesting. So I just thought I'd add this. So it's not exactly quantum, it is quantum, but if you ask me where the real innovation is, like yes, quantum technologies, there's a lot of innovation there, But all of that quantum technologies involve a lot of classical hardware, classical software, classical everything. And you already see that we always have to build a hybrid system, right? And actually, all of the quantum hardware that you're developing for quantum technologies, whether it's computation or sensing or whatever, they actually have other useful practical applications in other, let's say, industries, like in experimental control factories or just about anything. Because everything, like for example, if for superconducting quantum computers, you need to develop very, very low noise, ultra stable, ultra tunable microwave sources, so gigahertz, like our 5G. And consequence of that is like because you have to do that, then this actually has a lot of practical implications to our 5G, like our like Wi-Fi technology. So, it's a vicious cycle, right? So that's for me, that's really where the innovation is really coming from. Just to give you also a teaser, this is a picture. For me, if you really ask me, the real future is on AI, quantum as well. Don't get me wrong, but not because the thing is, all of these are connected. So, but AI, but photonic neural networks. So this is where you really use laser light to create a GPU. And there are actually startups that are doing this, and this is amazing because in this paper, for example, they made a photonic chip with only six photonic real photonic neurons, not like algorithmically programmed neurons, and they're able to do image classification with one like few picosecond like decision reaction time. That's insanely fast, like picosecond. That's insane. So there are a lot of startups, like for example, these last two, Aketonics and Light Matter, they are trying to do that. So it's an intersection between quantum, AI, photonics, because they are all really connected. And NVIDIA and AMD are in NVIDIA, for example, is investing heavily in photonics. And yeah, so that is the end of my talk. Please feel free to reach out if you need any information. I can still talk about any other things. Like I can give this talk again with a like specific topic in mind. Yeah, connect with me on LinkedIn, and you can also check my website. Thank you, guys. Are 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 there
Great.
people still there,
Awesome. Yeah.
or are they
Yeah.
sleeping? No, I'm kidding.
No, I think yung host lang ay na-disconnect. But great. Thank you so much po Doc Fritz on very interesting kasi usually kapag quantum, 'di ba, like algorithms agad, quantum computers and like the coding and circuits and stuff. So
Yeah,
we're glad to see the hardware side of it and the reality. To be honest, I like your talk since no BS, no no hype. But there's still optimism and
yeah.
really like that. So thank you so much, Paul. Guys, everyone, you still have a few more minutes to take some questions in so you can send them through the chat. So ako po, sir, I have a question. Sige, while waiting for the
Yes, yes.
others. What quantum sensors are most relevant to the PH, particularly yung mga use cases dito? Kasi I see some positioning systems, I see some gravimeters for oil, and I saw rin parang atom-based antenna since I'm from ECE background eh. So, parang may nakita akong ganun. So, ano po kaya yung mga pinaka-relevant for use cases here in the Philippines?
Yeah. Yep, yeah, yeah. That's a very, very good question. So I'll start with gravimeters because with gravimeters, you don't really need a lot, and it's easy to build. So I know how to build it. Of course, I don't want to do it alone. You can also buy it, but I'm more in favor of building it because if you build it, then you use off-the-shelf components. Then you also train students like with electronics, programming, everything, and you gain the know-how that this quantum hardware can also be used for other things, like the hardware, the techniques that you use. So And also for the practical side, gravimeters. Why? Because you can actually sense, like it's so sensitive that you can sense shifts in tectonic plates. And recently I'm from Cebu, like I was there during the earthquake. Was not a pleasant experience, and I'm sure that it won't be the last earthquake or flooding or things like that. So these things are actually measurable. So for me, like that's very, very practical because you can just put them in a few sites all over the Philippines, like strategically, and you just keep measuring, measure, measure, measure. And then like the more you have of those, and you create a distributed network, like maybe just 10 gravimeters, quantum gravimeters, you collect data and you can leverage AI to train. So now you would also have to collaborate with geologists because now this is going beyond physics or engineering. So it's interdisciplinary. So that's what for me, I'm really in favor of gravimeters. It's very practical for us. Like we will learn a lot about our geology, whether it's under the sea or on land. And the second thing is uh other sensors, like for example there are sensors that you can use like for chemistry, and of course like it's again the same thing, like the know-how on how to do it, like not just chemistry but also life science. But I will not touch on this because I'm not an expert in that. I only know of people that actually do it. But yeah, for me, close to my heart, I really want to do environmental monitoring sensing in the Philippines. Like actually that's what I tried to do before. But yeah, yeah, that's my. I hope that answers your question.
Awesome. Thanks for you mentioned it's an easy way to get into quantum, like for students, right? Like it's one of the kumbaga hello world, but if you want to build your own hardware, as opposed to quantum computers per se na need ng dilution fridge, right? Great. Yeah, we also have a question that medyo controversial. What do you
Yeah.
think about D-Wave? Are they true quantum computers or not?
So actually, D-Wave, when they first came out, I remember as a group, I mean, we actually reviewed their paper. So we were, so D-Wave is a, it's a thermodynamic system. So on the bigger picture, it is a quantum computer, but it's not exactly the quantum computer we hoped for. But actually, they pivoted. So they are doing something practical. So yeah, but nonetheless, I don't really know. So yeah, I let's say I'm neutral.
Awesome. All right. Okay, so we have a question from Kyle. Hi, sir. Just want to ask for your career advice for someone who wants to start a career in the field of quantum.
So question is what kind of quantum? Because if you want to do nowadays, you don't really need to be a physicist to deal with quantum. So if you're interested in software, because now, like as you know, if you've seen, like a lot of software is now integrating quantum, let's say like PQC, post-quantum cryptography algorithms. And the startup that I was actually, I was advising a startup based out of UAE, and they are actually it's a cybersecurity defense related company, and what they're doing is actually they're leveraging quantum computers to generate random numbers, because you know that random number generation is not a very easy task, right? So like if you generate random numbers with your classical computer, there it's not really so random, so you can be hacked, right? So your honeypot system, so your cybersecurity algorithms. So you have to use quantum computers to generate random numbers. And I actually told him, like, why do you have to like access that quantum computer? Just generate the quantum random numbers generators yourself. And there are companies that sell just random number generators that are quantum inside, ID Quantique, for example. So yeah, but if you want to deal with hardware, like if you want to follow my path, then you really have to study physics. Uh, I would suggest though, like if you want to deal with the hardware, electrical engineering is a good start. Because nowadays, like for me, there is no distinction between all of the engineering sciences. Like I have a good friend who I worked with in the startup. Like we're both physicists, but his background was an electrical engineer. But then he turned into a physicist. So, all of these paths are crisscrossing. So you can even be a computer scientist and you're just so smart with math and you deal with all of these algorithms that you do a PhD in quantum algorithms under a physicist. Like it happens often. So yeah, first figure out which path you're taking, and if you need advice, reach out to me. Like I can point you in the right direction, and yeah, hopefully I can help. Yeah.
Awesome, great. I think Kyle is from the computer science background. So, yeah, awesome. We have question from Maxil. In the field of bioinformatics, are there any possibility quantum can help on that? Are there any research already?
Wait, say again. Say that again.
In the field of bioinformatics, are there any possible quantum use cases for that field?
Bioinformatics. Ooh, that is a very good question. I should ask my bioinformatics friend. I'm just speculating, okay? So what I'm going to tell you is just speculative, and yeah, take it with a grain of salt. Uh, Phew. Actually, it's a very good question. So again, I think I will go back to the answer. So this is probably not the answer that you were asking for, but uh, because like in biology, especially protein folding, but this is not really bioinformatics. Like there are a lot of biological processes that have a lot of quantum mechanics in them. So that's why there's also biophysics. And yeah, and there, like in quantum chemistry, quantum computers benefit because of quantum computation, but bioinformatics per se, I'm not really sure. I'm sure there is. I'm really sure there is, but yeah, I don't know.
That's fine. Thank you, sir. I think that's another point for contact for all of us. Yeah, great. Another question from Vincent. How can quantum integration expand the method of chemical gravimetry and the limit of detection of atoms and molecules? I think the question is how can quantum help in increasing the sensitivity of our sensors?
So the thing is, with a quantum sensor, for example, a gravimeter, you know what you know what you're doing? You are measuring the interference of matter waves. So you're physically taking these atoms, you're laser cooling them, and when you laser cool atoms, they lose their identity. So they become like one big super atom, which is called the Bose-Einstein condensate. And what you do is you split these atoms and then you split them and then you drop them, and as they drop you combine them again, they interfere, and what you really see is you see interference patterns. And if you know what interference is, it's basically a wave phenomena, and here that's really what you're measuring, and that alone you can actually it the how would I say this? I'm trying to find the right explanation without confusing everybody. Basically, this is a quantum effect that you're using, and inherently on its own, it's just much better in sensitivity. So yeah, I hope that answers your question. That this is really this is a very this question requires a longer time to explain. So yeah.
Awesome. Great. We have a question from Lawrence and Paul. Na-inspire daw po sila. So,
Good to know.
something more personal instead. How do you approach studying? And from Paul naman, do you ever feel frustrated at some point and how do you handle it?
Ooh, so this is a personal question. So yeah, so for me, I think the people who know me as like a very, very dedicated, motivated, and determined person. But yeah, what kept me sane was my hair losing. I'm kidding. No, but actually find a hobby or outlet. I guess it's a personal, like, preference for each person, but like life is just not about like, of course, physics or your work, whatever your work is. So you have to find some outlet that just makes you, let's say, you can use to, yeah, learn, how would you call this? Uh, Release. And if you can find a hobby, I mean, this is very, personal, find a hobby that also connects to your work. So I like playing guitar music, like I also like building electronics. So they're all related. So I'm just really a nerd, if you call it that way. And so yeah, what I do for my hobby complements my work. So it's a win-win situation, So yeah.
Awesome. Nung ine-edit nga po namin yung mga publication materials for you, we saw your photo like climbing nasa bundok, mountain top,
Yeah,
and
yeah.
climbing on a ledge. So
Yeah,
yeah.
yeah.
Saan po
I
yun?
like
Saan po
outdoors,
bandang
rock
part?
climbing, mountaineering. So yeah.
Awesome. Amazing. I think, yeah, siguro last question. How much quantum technology can help on the field of neurotechnology?
Neurotechnology. Neuro, by neuro you mean like the brain?
I think so, sir. Yes.
So
Ayan,
yeah,
yes, yes.
I see the question. Yeah, actually, interesting. So this is a very, very I don't want to be stoned by the physicist. So there in biophysics, there is actually there are actually a group of physicists and biologists that are trying to study the quantum effects of the brain because all of those, impulses, synapses, they might be related to quantum fluctuations. So maybe consciousness is related to like quantum fluctuations, but yeah, to be honest, this is way beyond what I know. So and it's also highly speculative, but technology, since you asked technology, MRI actually, because there are already quantum sensors that are already embedded in MRIs. So they are just so sensitive in detecting magnetic fields. So you can actually sense the brain much more precisely. I saw a question here, so I just saw the question and answer portion. QKD is somehow not yet accepted in the banks, just that. So quantum key distributions, actually, yes, it is, but not in the, I don't know in the Philippines, but yes, it is in most banks, like very top tier banks. So it's an optical cryptographic way of exchanging keys. So yeah, sorry.
Great. Awesome. Ayan. So, thank you daw po. Ang daming mga nag-chat dyan. Thank you so much. And we
Thank
hope
you
that
as well.
we have the opportunity to meet you daw po, sabi ni Paul. So, yeah, I think we're already entangled. So, siguro, if nandito ka, sir, please let us know para we set a meet up with everyone. Okay, great. I think it's already time, so let's wrap it up a bit. Let me ask Kyle to share the screen again for the certificate of appreciation. Maraming salamat po, Doc Fritz, on entertaining our request. I know you're super busy. Anyan, thank you po sa ano. Nasa Singapore po kayo right now, right?
Yeah, yeah, yeah. I'm in Singapore, and
Awesome.
if somebody's coming here, like just write me a message.
Great, awesome. Yeah. Okay, so the certificate acknowledges that Dr. Fritz Diorico has masterfully shared insights as a speaker in the World Quantum Week Spotlight Talk, a webinar in celebration of World Quantum Day, signed by Engineer Ethel Joy Bajang from IEEE Computer Society Philippines and Sir Bobby Corpus Jr., the President of the Quantum Computing Society of the Philippines. Again, maraming salamat po, Doc Fritz, for sharing your time and
Okay.
your expertise and inspiring us, I'm sure. So, I think mula kanina mga 50 yung nag-attend, baka one of these people will be uh, future quantum sensor researchers. So, okay, great. Thank you po for,
Thank
again,
you.
yan,
Thank you,
may visit
everyone.
daw po yung SC Cebu Department of. Thank you po.
Ah,
All right. All right. Thank you everyone for staying with us until now. We know that 3 hours of back-to-back talk is a lot to take in, but we hope that you enjoy. We still, meron kaming evaluation form right after this slide, so you can tell us what you experience and what can we improve for the next sessions pa. So we hope that you enjoy the rest of the week. So tomorrow we will have a talk on quantum plus AI, and then the next sessions, Friday, will be on photonics and iba-iba pa, no, in quantum key distribution rin meron tayong talk doon. And on Saturday we will also have some talks on cryo CMOS or control electronics. We will have a someone talk about quantum applications in the energy sector, and some other people that will also talk. So yung mga hinanap po namin, hinalungkat namin are all Filipinos, Pinoy. Talagang hinanap namin sila to show and to tell you guys that may utak tayo for quantum. So that's it. I think we can conclude our talks, our series of talks for today. If you want to connect with our speakers, you can search them up on LinkedIn, or just let us know, send us an email, and then we can send your email to you. And yeah, hoping that we will have more conversations like this in the next few days. Again, maraming salamat po. Magandang gabi sa inyong lahat, and happy World Quantum Week. Doc Fritz, maraming salamat po ulit. Bye-bye everyone, and have a great night.